Thank you. All right, let's go ahead and get started. So happy Wednesday. So we're just finishing up kind of chapter 4 today. So going over the polar molecules part, and then we'll talk about organic structures briefly. So of course, ask questions. Today's a good day to kind of ask questions on anything. But let's start with polar molecules, unless, like I said, there's any questions that have come up. But maybe let's start with the definition of polar molecules. Does anybody have an idea of what a polar molecule might be? So, yeah, I mean, kind of. We'll put, yeah, yeah. Yeah, that was a really good definition. Sorry, let me just shut the door. So that was a good definition. So you said uneven distribution of electrons, and then now I forgot the second half. So did you say like resulting in? Yeah, I like that. So resulting in polar regions, which again, we'll just make sure we're not using the definition in itself, but just uneven, or we'll say, right, so that means more positive and more negative regions. So let's look at some examples, and we'll kind of, again, go back to what this means. And so let's compare 3 molecules here. So let's look at methane, and then let's compare dichloromethane. Put on the electrons for good measure. And then carbon tetrachloride. So I'll let y'all just kind of look at these for a second and what you guys think, and then we'll go over. So looking at these, what's kind of the difference between these 3 molecules? What do you notice? We could kind of talk about symmetry for a second. And we're also trying to answer, so which ones are polar, which ones are nonpolar, and kind of why. And there's other ways to think about polarity, which we'll get to right now, but
So methane and carbon tetrachloride would be nonpolar because they're equal on all sides.
excellent. And so I don't know how people's brains work, whether that's like obvious or not. So the other way to kind of think about that is you can what's called like add the vectors, and it depends like how much physics and math that you've had with like vectors, where either that totally makes sense and you're like, yes, that's great. Otherwise, I would say like try to look for unevenness. So, right, like we're comparing methane and carbon tetrachloride. Well, our methane has all hydrogens all around, so that's pretty symmetric. We could try to draw arrows. Of course, this is pretty non-polar anyways. So I would say these are pretty non-polar bonds in itself. So overall, really non-polar. But let's draw vectors for these. And so I'm going to draw them where the arrow is going towards the more electronegative element. So that might be opposite from your normal physics convention. But if we compare the dichloromethane now to the carbon tetrachloride, so again, we can draw out our vectors in all directions. And it might be useful to pull out your molecule kit. So I have two versions. Sorry, I was just trying to get a little tetrahedral. So I'm just looking at the tetrahedral shape in itself, right? I do have larger ones. So again, kind of tetrahedral shape. And so it's going out in all directions evenly, so it would just cancel out like you guys figured out. So yes, our carbon tetrachloride is nonpolar. And so we can use like the compound chem sheet too to help us. So let me pull that back up. And so generally kind of the trick that you'll notice is if we have, so the first row, or excuse me, first column here is going to be what I call the fully symmetric geometry, right? So if we have like this atom for instance, and we have two of the same, right, that's going to cancel out for our vector. Same thing with our trigonal planar, again, right, fully symmetric going out in three directions. So if you have, again, the same or very similar in electronegativity atom, that would result in nonpolar. But anytime you move over here and you've broken the symmetry, right, so now you have a lone pair, well, that's a good suggestion that it's probably polar. So now we have that lone pair there. So it doesn't matter what these substituents are, right, still polar. So same thing, tetrahedral. So as long as we have the same atom on all four, again, that's going to be nonpolar like methane and carbon tetrachloride. And then if we break the symmetry, so let's look at two examples, right, of breaking the symmetry. So do we remember what's our example of our trigonal pyramidal geometry typically? What's the classic small molecule? You made it in lab today. You generated it. Yeah, ammonia. So ammonia now is from our tetrahedral family, but it has a broken symmetry, again, from our lone pairs. And so we could also, again, get into the geometry that these lone pairs are occupying a little bit more space. So they're pushing our atoms a little closer together, so we can, let's zoom in and appreciate that. So just comparing bond angles, fully tetrahedral is 109.5, and then again the lone pair occupies a little bit more space, just repulsing, and so then that makes this angle a little tighter at 107, and again we've broken our symmetry, and so now we would say that ammonia is polar then, right, from again our lone pair. So we could draw out our electron density map. And so let's also look at this in the context of another measurement. And so again, this is kind of like for fun fact and to help you if you were to continue on your chemical journey. So you can also look at what's called the dipole moment, at least assuming it's reported. It usually is on Wikipedia. Where's my dipole moment? Oh, there it is. So dipole moment. And so you have to put some context to it. So this is kind of fairly polar at 1.42 for our dipole moment. And so let's look at a few other compounds. So let's pull up something nonpolar like pentane, or we could look up carbon tetrachloride. And again, just kind of put context to these values. So pentane, pretty nonpolar molecule. So let's double check the dipole moment. Water is going to be polar, so we'll look at that. Do we not have a dipole moment for this one? Okay, never mind. Let's try carbon tetrachloride. So carbon tetrachloride dipole moment of 0. So right, just what y'all predicted. And so let's look at water. It's a measurement of like basically I forget actually what it measures. It's like a measure of its springiness, but it's basically how polar it is. Is what it's like. Yeah, so 0 would be perfectly nonpolar, and that's why I was trying to put some context. So water is fairly polar, and so it has a dipole moment of 1.85 there. And we can draw out water and understand why it's polar, right? So tetrahedral base, but now we have 2 of those substituents replaced with our lone pair. And so again, that creates a region of electron density on that one side.
So something like square, planar, and linear, the 180, where it gets the 6 electron pairs, those are still going to be they're still going to be polar.
Well, now some of those might be like non-polar. So if you did it, that is kind of confusing because you could do argon tetrafluoride there. And even though it has those lone pairs, those kind of cancel out. And then same thing with all these fluorines. So let's see if it has, because you got me curious what its actual measured dipole moment is. Oh, xenon. I should have looked at xenon. So I would expect it to be pretty. So yeah, it actually does have it of 0 from, like I said, probably those lone pairs canceling, and then it probably helps that like fluorine's really electronegative compared to the lone pair. So it's all, I would say probably all the outside is like full of electron density, but of course canceling out. So yeah, there's a few tricky scenarios, but otherwise we're like looking for broken symmetry like water. Another good one to look at the dipole moment of, to give you context, would be something like acetonitrile. So this is considered fairly polar. It might make more sense if I wrote it out better. So let me rewrite it so you can see the electrons. So we have this nonpolar CH3 group at the end, and then we have a carbon triple bonded to nitrogen. And then that nitrogen has a lone pair on the end, right? So then that makes it pretty polar because we have one end with this high region of electron density. And then let's compare the dipole moment experimentally. And so this one is close to 4, so about 3.92. And so that's kind of what we'll see, right, for our range of just like normal compounds. So I'm not sure like what the theoretical range of the dipole moment is, but this would be considered, like I said, a fairly polar molecule at almost 4 for our dipole moment. We saw about 2 was kind of polar, right? So again, going back to ammonia. So that was 1.42. So again, right, that's more polar now, so considered polar. And again, water was like 1.8, we said, I think. So 1.85. So again, just kind of giving you context, right? Because there are a few weird things, and I mean, we can. Sorry, I was trying to pull up. I didn't do a good job. I was trying to find just a quick epoxide, because some of these have lower dipole moments, but you can see they're like kind of polar from this weird ring thing. So there we go. Ethylene oxide will help us. And so something like that, so that does have a fairly high dipole moment of 1.94. I was trying to find something a little lower, but again, it just kind of depends on your full geometry there. But again, we're just kind of in the learning stage, so putting context to things. So let's see, what are other good examples? Oh yeah, so let's look at this one then. So what about sulfur hexafluoride? Is that polar, nonpolar? So take a minute for that one. So do we all agree? Right? Yes, no, nonpolar, polar. Yeah, so it should be nonpolar, right? So again, even though it has all those fluorines, they're going out evenly. We could go back to our compound chem example. Of course, now I lost it. There it is. And so it is, right, our fully symmetric one. So that kind of helps us. So yeah, I would expect like our square pyramidal complexes, those would probably be polar. Like we mentioned, the square planar gets weird because that might cancel each other out like we saw. And then T-shaped I'd probably expect to be polar. Can look up some examples. Let's see if we can find a measured value. I think IF3 is more accessible. So let's see, doesn't have a dipole moment. Let's look it up. I'm sure it has to have a dipole moment somewhere. Wikipedia sometimes lets us down. So according to the internet, right, it's about 0.632. So not the most polar, right, but kind of, again, we can surmise those lone pairs are definitely contributing to some polarity. So again, just putting context to things. So what about, let's look at acetone for a second. So this is kind of the shorthand for acetone. I could redraw it a little better. So write those sticks. So we want to start recognizing what it is if I were to draw it like this or like this fashion. So anytime you have a point here, that's a carbon. And again, carbon needs 4 bonds. So then we know it's this methyl group. All right, so then tell me polar, nonpolar. Take a minute for it, and then we'll. So I have 1 vote for polar. Do we agree? So nice. So polar. And it would help, right? I didn't draw in the lone pairs, but if we add them in, that kind of makes it a little more obvious too that that's polar with those lone pairs there. And then Again, we don't want to get too excited, but I would say that this starts hinting at reactivity. So we have this negative charge over here. So that means this carbon is a little partial positive, kind of susceptible to electron attack. So that would bring us into OChem reactions. But like I said, we don't want to get too excited. I'm just kind of saying, right, you can lay down a lot of fundamentals just from these little tricks here. All right, so let's look at, so what about this? So we'll do this one and this one. So polar, non-polar for both of those. I'll throw one more on there. So P, Cl5. So again, polar, non-polar. Obviously, I didn't draw this one out, so you may have to. So again, take a few minutes. And so if you're in online, feel free to post answers in the chat. So you said we thought this one was polar, so did we agree, disagree? Okay, so good. So a lot of people agreed that it was polar. So we have this OH group. And again, we can kind of put properties together, right? So this is polar. And so this is ethanol, right? So 1, 2 would be ethane. Not that we've gone over that, I'm just saying that it's ethanol. So we're not getting into organic naming in this class. But okay, so it is ethanol. And then if you remember, right, ethanol is miscible with water. So that makes sense. So that kind of goes into, if you remember the saying, right, like dissolves like, which kind of gets into our demo too, because some people are asking like, oh, well, would the light bulb demo work with another solvent? And my answer was, well, it would have to be another polar solvent, right, that would be able to solubilize those ions, because that was the whole point of the light bulb demo, is that, right, our water is polar. Oh, sorry, that's maybe, I was trying to draw the jar, but now you can't see anything. So let's make that bigger. So we have, right, again, our water. So thinking about what happened with our salt solution. So we have our negative side, right, again, from water being polar. So if this side is negative, and we could even draw like a partial, so that's this little like gamma symbol. Sorry, let me scroll over. So that means partial. So basically we have a partial negative on our oxygen, partial positive on our hydrogens. So then let's just take sodium chloride. So right, the sodium then will be more attracted to this oxygen N, and then the chlorines will go, or chlorides will go over to the hydrogen N, and that's how we get solubilization, right? So there has to be some sort of attractive electrostatic forces there. And so yeah, we would need something that's also polar. So maybe ethanol, right, would work. I'm not sure, because now we get into, well, how much salt can we dissolve in ethanol? But I would expect it to be somewhat solubilizing, right, because it is polar with those groups there. So just kind of things to think about. And there are other organic polar solvents, but like I said, we won't go down that rabbit hole, but that's just where your mind would be if you were an organic chemist. Oh, and kind of more things to think about with chemistry and polarity. So this is kind of a fun fact that is developed recently. So going back to dichloromethane, so this is, I call it one of the workhorse solvents of OChem. It's beautiful for so many reasons. So A, it's polar, as you guys figured out, right? So that means it dissolves a lot of stuff, and it's super dense, which can be useful for distillations because normally organic solvents are less dense than water. However, there's been a huge change, and it's somewhat dramatic for the chemistry world. So dichloromethane is kind of toxic. I've never experienced this because I didn't work with it enough. But if you are like a workhorse organic chemist that is working with this a lot, what can happen is overexposure. So if you get like DCM on you, you know because it burns and it goes straight through your glove. And so you just kind of rip off your glove and wash your hand the best you can. But over time, there are some organic chemists that, like, if they're even exposed to the vapors of it, their hand burns, and like, I'm not quite sure what that is, but that's why that this substance has kind of, I forget how it got classified, but they're trying to like basically outlaw it from research labs and obviously like teaching labs, and so now that's created a lot of issues, and so now they have to find alternative solvents that aren't as toxic. And like I said, I'm not exactly sure like the biological mechanism of what makes it burn. All I know is every chemist knows the DCM burn. Anyways, just fun facts to think about solvent picking. So polarity matters. All right, so going back to HCl, so what did we agree on this one? So polar and good, right, same thing. So you saw me mixing the HCl this morning, and so of course it was miscible in water, so I did dilute it right with some water. And again, polar, like dissolves like. What about PCl5 here? Excellent. So nonpolar, and right, maybe we had to sketch this out just to, again, appreciate that all the chlorines cancel out there. So even though the individual bond, right, is polar, overall nonpolar. And then again, right, you'd want to dissolve PCl5 in like some organic solvents and something nonpolar, hexanes. So typical nonpolar solvents, I'll just list a few. So hexane is usually used, but I'm going to say that hexanes are toxic, so be careful with that. It's only long-term exposure, so I've been like phasing them out. But pentane is safe, so you just don't want the six-chain carbon. So the six-chain carbon makes a biological byproduct that is the same length as like your neurons, and so then that eventually leads to like motor dysfunction and other issues over time. But again, that's long-term exposure. But pentane and heptane are fine. And so those are kind of the common ones. And then we start to get, down the row of like how polar do we want things. But again, we won't go that far down the rabbit hole in here. All right, so let's switch to looking at these organic structures. Well, let's start with something a little simpler before we look at those big molecules. So for our organic structures, kind of the main thing to keep in mind is that carbon needs 4 bonds. And then, right, you fill in with hydrogen. So let's compare these two examples. So what is the formula if I draw this molecule? So again, every point is a carbon. Fill it in with 4 bonds versus this one here. So again, see if you can draw out or figure out the formula. So we'll start with these. So let's look at this one. So nice. So C6H12, and I'll redraw that for everybody. So just so everybody's on the same page, right? Every point is a carbon, so I'm just going to redraw it like really explicitly. And then, right, excellent job on filling in the hydrogen. So we just have to fill in all these carbons with 2 hydrogens. And then, of course, count them up to get our formula. So C6H6. And so it's only the hydrogens on the carbon that are not drawn explicitly. So we'll look at other molecules. But if you have like we saw with ethanol, for instance, right, we draw in that OH. And then, right, you could fill in the formula for ethanol here. Or like acetic acid, for instance. I'm just throwing out examples. So in those cases, right, you will draw the hydrogen explicitly, but not on the carbon. So then what did you get for this structure? Excellent. So C6H6. And so again, this one could have been tricky. Maybe you want to kind of redraw it. And then what's kind of weird about this, so this is called an aromatic ring. And so that means that these electrons actually are delocalized across this whole ring system. So you could draw it alternating like so, or you can draw it where the double bonds are look like they're on other carbons, or you might see it abbreviated like this to kind of show that it's delocalized aromatic pi system. And then 1, 2, 3, right? So again, that's how you got C6H6 there. And then this is kind of beyond this class in some ways, but I still think you could appreciate it. And so I want to point out, right, it's kind of deceptive if you draw cyclohexane like this, because it's not actually flat. And so it's more of this, and now we get into OChem. So it either comes in this chair conformation or boat if it's more strained. But again, all I'm saying is it has 3D character, which isn't really shown in that picture, versus benzene. Oh, what did I do with benzene? So benzene is actually flat. And it's kind of the difference between the diamond and the graphite, like we mentioned. So again, same concept. So where the cyclohexane that we saw has 3D structure, just like our tetrahedral diamond, versus our sp2 benzene here, right, where it's flat. And so you can kind of see it from this picture a little better, like it is flat, just like your graphite, right, is flat in sheets. So again, just somewhat appreciating the geometry. Like I said, we don't need to get too far down a geometry rabbit hole today, but I at least want you to be aware, right, that like you draw things in chemistry and it may not be giving you the full picture. So you kind of want to always be thinking in 3D for chemistry, which is hard to do. That's why I'm like, it's kind of beyond the scope of this class, but I want you to be like thinking about it so you're not completely ignorant.
So, in the aromatic ring, you were saying that the electrons are localized between like every single bond. Like they could be anywhere within that.
Yeah, within this whole like ring, because if we were to get into it, so it's like this pi system, and so this pi system is all empty, and so the electrons not empty, but they're all in phase, it's called. So then they all like run around, and it's this whole delocalized pi aromatic system. But yeah, we just represent it with the alternate bonds or like so, or yeah, those are like the two main ones. But yeah, and the aromaticity makes them fairly stable as well. So, but that like I said gets into like OChem reactions, which all right, try this challenge. So, this is one of the conformers of THC. And so again, right, count out your carbons, fill in your hydrogens. So I'll give you guys a few minutes to try this one. Good practice, right? You might want to redraw it more explicitly. So keep working on it. I'll just kind of start sketching out where everything goes. Then of course double check me. And then notice, right, they did show this hydrogen explicitly, so that's just because they're trying to show stereochemistry. So what do we get for the carbon count? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Is that what other people got? Double check me. And if you were doing this in OChem, so, I mean, I keep talking about OChem, but I don't know if you guys will get there. But if you do, the most important thing is counting. So, right, you can do 1, 2, 3, 4. Like, do not be ashamed to count and label them. 9, 10. So I'm just kind of showing 14, 15, 16, 17, 18, 19. Oops, yes. I don't know how to do 19, 20, 21. So just double counting. That's like my biggest advice for OChem is count and then count again. All right, so help me with our hydrogens here. What do we get? And so I just filled them in. Then, of course, right, that didn't have any. 1, 2, 3, 4, 5, 30. That sounds right, but so sorry, I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So I like that count. Did people agree with that? Might need a double, triple count on that one. And so usually it goes carbon, hydrogen, and then kind of in alphabetical order. So like nitrogen, oxygen, and then other heteroatoms. So we're just left with oxygen. So how many oxygens do we have? So two. And like I said, this is just kind of the general formula. People tend to group atoms like you already saw with the acetate, right? So kind of grouping them based on like function and group. All right, that looks good. So try just regular amphetamine. So again, I'll give people a few minutes. So I filled in the hydrogens. So don't forget about this little one here. And so let's see, let's count it together. So what do we get for carbons? So 1, 2, 3, 4, 5, 6, 7, 8, 9. I like it. So C9. And then how many hydrogens? So let's 1, 2, 3, 4, 5, 6, 7. And then 8, 9, 10, 11, 12. Okay, we can always recount. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, 11, 12. Now I get 13. Oh, okay, so 13. So like I said, right, count, then recount. That's like the hardest thing in chemistry, honestly. And then looking at our heteroatoms, we just have nitrogen left, and it's just one. So it looks like C9H13 there. Good. Any questions on kind of the structures and interpreting them?
Are you gonna have tests where it's like fill in the blanks with these structures?
I might have like a formula thing. So yeah, like there might be, and I'll try to do something simple. Like that was a little much, right? So try to keep it maybe this complexity or easier on an exam, and then it would just ask you what's the formula.
Oh, okay.
But yeah, I don't expect you to obviously name these either, because like I said, we're nowhere near organic naming. All right, I think that's about it. Unless, like I said, there's questions, we can always go back and touch on any of the naming if anything came up. So just remember, right, your like again, for our purposes, zinc is always 2 plus, and silver is always 1 plus, which is kind of tricky because especially if you look at the periodic table that you were handed, right, it does have all different oxidation states, and different oxidation states do exist of silver, but like I said, for our Gen Chem 100 level purpose, we're just saying silver is always 1 plus, so we don't need to name it, right? So again, that means like AgI is a silver iodide, so we don't need to say like silver 1 iodide. We're always going to be dealing with 1 plus in here. But I think that's all that have kind of come up for questions. All right, so I'll probably stop the stream then. And then I do have the paper quiz if anybody wants to take the paper quiz in here. Otherwise, I know people have taken different variations online. I do have some molecule kits if you want to play with that some more. Otherwise, right, use this time to do work, ask questions. Otherwise, obviously, you're free to do your thing. And then if you're online, just ask me questions.